this is the second lecture on using Python for linear algebra applications, and today we're going to look at matrices. So as usual, I'm importing the necessary libraries and I'm defining this function, define show, which is basically going to show matrices or vectors basically in nicer sort of fashion. Okay, that's all it is. Now, let's go and create a matrix. So I'm creating mat matrix using np.random.randint, choosing values from 0 to 20, and the tuple follows with the dimension of the basically matrix of random integers that I'm creating. Okay, so mat is created, and I'm going to now use this function show to visualize my matrix. And this is the random function that we generated here. So let's look at some terminologies. The diagonal elements of our matrix. So in this case, the diagonal elements are 0, 2, 2, 0, 2. Okay, and how can we extract that with Python? So mat diag, meaning the diagonal elements of our matrix, use the np.diag function. Okay, so np.diag, and then in the parentheses you feed in your matrix, and it will extract the diagonals of that matrix. So if I do that, I'm gonna show diag. It's basically going to that to be your diagonals of this particular matrix. So this is the function to extract out the diagonals. Okay. Now one thing you need to also bear in mind, yeah, if I now have my mat diag, yeah, so I have now pay careful attention here. So if I go here and I say sorry, um, sorry, yeah, yeah. So if I just call mat diag, so that's an array of my numbers. Now this np.diag works in two ways, yeah. If I call np.diag of these numbers, just look what it's going to give me. So it's going to give me a matrix of basically zeros, except that the diagonal elements are going to be basically fitted into that, zero matrix that you created. So just pay attention that the np.diag can either extract the diagonal values from a matrix, or if you give it a series of numbers, it can generate a zeros matrix where the diagonal elements are those diagonal elements that you have fed into it. So this would be quite useful, basically, especially with certain operations that we will check in future. Now, regarding shape of a matrix, just like vectors, we use the dot shape function. So our mat was, it's a 5 by 5, of course. Yeah. So that was our matrix. It's a 5 by 5 matrix. And we use the dot shape. So we have 5 rows and 5 columns, n by n. Now, certain terminologies which I'm sure you should be aware of: the column space of a matrix, which is defined by the number of linearly independent columns of the matrix. Now, I hope that you understand what linear independence means. So if you go back to the lectures on vectors, basically each of these, let's say the column vectors of the matrix, do they have any linear relationship? Meaning, can you get from one column to another by doing some form of linear operation? If you can't, then you would say that those columns are independent linearly from each other. And that is a very, very, very important topic in linear algebra. And of course, the same applies to rows. So the column space of a matrix or the row space of the matrix, same definition basically. If you can get values, associated with one row, can you do a linear operation and get to this another row basically, or no? Are they linearly independent? So these are very hot and important topics in linear algebra, and I really expect you to well fully understand them. Now there are several classes of matrices. You can have a square matrix, a rectangular matrix, a symmetric matrix, which only applies to square matrices, of course. Skewed matrix, identity matrix, very important. The zero matrix, where everything is zero, and of course, identity matrix is a zero matrix with its diagonal elements all being one. Okay. Then you have the upper and lower triangular matrices. These become important when you look into more complex topics such as QR decomposition, which will be in later videos. And of course, a diagonal matrix, which we just basically looked at an example of one. Okay. Now, as an example, let's just for visualization, we're going to make two matrices, a square one and a rectangular one. A square one, basically, we're going to use the random.randn function and to generate a 5 by 5 matrix, normally distributed sort of set of numbers from from -1 to 1. And the rectangular one is going to have shape of 5 by 2, meaning 5 rows by 2 columns and 5 rows by 5 columns. So we make our matrix. Now let's use the function to visualize it. This is our square matrix, basically 5 rows, 5 columns and 5 rows. And a rectangular matrix, which is basically having 5 rows and 2 columns. Okay. Now identity matrix, how to make an identity matrix with numpy. Use the numpy.i function, and depending on the size, obviously the identity matrix is going to be a square matrix, so you just give a single number which is going to be working for both rows and columns. So I equals np.i5 means that generate a identity matrix which is a 5 by 5. Okay, and then we're going to straight away show I. So that is it, the matrix. This is identity matrix of 5 by 5, and we got ones in the diagonal. Now np.zeros, you need to define the size of how many rows and columns you want. So you use the function np.zeros, and then right away I'm going to show it with using the function shows that. So that's a zero matrix, and that's how you generate a zero matrix, and that's how you generate an identity matrix. Okay, so nums equals np.random rantin. So what do we have here? It's basically Google is taking its time. So I have basically, I just covered this earlier on when we were working with diag. Yeah, so I've generated 5 random numbers ranging from 0 to 5 random integers, and assuming that I want to create a diagonal matrix which basically has these elements, so I'll use np.diag_nums. Yeah, the numbers that are generated here, I'm feeding it to the diag function, and of course, as we just saw earlier, we're going to generate a diagonal matrix as such. Now we can concatenate matrices together. So let's look at this a bit further. So I'm creating matrix A and matrix B. Matrix A is, again, I'm choosing numbers from 0 to 10, randomly selected with the shape of 3 by 4. And the B is an identical one, but obviously would have different random numbers. So that's for matrix A. And this is our matrix B. Now we can see that they have the same number of rows, but different number of columns, okay? So we can concatenate these two matrices together along the columns, basically, yeah? Well, or like we can stretch it across the rows, right? How do we do that? We are going to use the np.concatenate function. Now, when you use this function, you just need to be aware. So use np.concatenate. First, you give basically in the tuple the matrices that you want to concatenate. What you need to define the axis. Yeah. So axis equals 1 means that go and extend the columns. Okay. And if I use axis equals 0, it means go and extend it across the rows. So let's just see what do we get. So as you can see, we got the first matrix, A and B. So B is basically has come and stretched the A, column wise basically, has added to the columns of the matrix A. Now, if I use 0, that should be doing it across the rows, but I'm going to get an error. And because these two matrices are different in terms of their, row and column size. So if I had matrix B as, like exactly same shape, similar number of basically columns. Now, if I do it, you know, trying to extend it, like attach this at the bottom of the original matrix. So I want to now go to extending the rows. So extending the rows, you use axis 0, and extending the columns, you would be extending across the columns basically, so you would be using axis equals 1. So just be aware of that. Very important, you need to give this axis parameter. Okay, matrix addition and subtraction is very similar to what we covered in vectors. So let's create K, a matrix of 3 by 4, randomly selected numbers from 0 to 10, and our L, which is going to be a similar size matrix, similar in terms of both number of rows and both number of columns. If you want to do addition or subtraction, it's important, it's imperative that they are exactly the same shape. Yeah, you won't be otherwise be able to do addition or subtraction. So adding them, basically it's performing an element-wise addition, subtraction, element-wise subtraction. So, but just bear in mind that like you're having K minus L, so it would be regarding K 2 with 0 K here. So it would be 0 minus 2, so it would yield 2, for example. So as I said, just element-wise, and the order by which you put these is important. And of course, if I do L minus K, in terms of the order, well, of course, it goes the other way around. Okay. Now, matrix scalar multiplication, again, very similar to vectors. Same rule applies. Basically, you just get an element-wise multiplication. So let's look at our math. We have just created a random matrix here, and I'm going to multiply this by 5, 5 being the scalar. And if we show it, so 5 multiplied by every single element, in this matrix, or like show math by 5, of course you get the same thing. Yeah. Now the matrix transpose, which is a very, very, again, important operation when it comes to further sort of more complex linear algebra operations. So let's just look at our matrix that we just created up here. So this is a 2 by 3 matrix. Yeah. So if I do math.shape, I'm going to be getting 2 rows and 3 columns. Yeah. So we can use the transpose as we covered in the vector section, or we can use the dot t. So I'm going to transpose this, and let's see what do we get. Okay. So if you notice, the way the transpose operation works now is that you can think of every single row being treated as a vector, and it's getting transposed. So you have 17, 11, 16 goes and turns into the first column, and the second row is converted to the second column. So just remember, with the transpose function, or applied to a matrix, you are going to have rows converted to columns, or columns converted to rows, basically. Yeah, same way. So think of it like that. Yeah. Okay. And again, I'm just trying to emphasize that you can either do np.transpose, or you can do math.t, capital T, of course. Yeah, same thing. And of course, transpose of a transpose would yield the original basically matrix. Yeah, so hoping that you understand what that means. So We have our mat here transposed. So original mat, let's just do it. So our mat was 17, 11, 16, whatever. So if I transpose it, I will get this new matrix, which is different shape. But if I transpose it on top, I'll get the original matrix back. Yeah. Okay. Now the diagonal and trace. So let's have a matrix, a square, and matrix R basically, just let's say two matrices, yeah? And they're different sizes. So let's look at math, yeah? Obviously, we know how to extract diagonal elements. Now the trace is the sum of the diagonal elements, yeah? The sum of the diagonal elements in a matrix basically is a trace of that matrix. So that is it, yeah. And you need to bear in mind that this trace concept really applies to square matrices. But if you run this, if you run it on the rectangular matrix, you still would get the diagonal elements, except that diagonal elements are going to be 15, 16, 5, 14, 0, and you're missing the 9. So really the trace, which is the sum of these diagonal elements, is only applicable to square matrices, yeah? So just bear that in mind. Right. Now, how do we get the trace? Obviously, we're going to do sum the diagonal elements, and we use the numpy sum function. So here, what have I done? I'm running the np.diag on the matrix R, basically. Well, it's the rectangle one. I really should go with the square one. And if I do that, I'm going to get 38. Or alternatively, if I do it like this, I'm going to get the same. Okay? So np.trace is the numpy method of extracting the trace. Now let's check out the rectangular one. We're getting 40, and what am I going to get if I run on the automated one? Obviously, it's going to give you 40. So just be aware that, you know, like the trace is really related to a square matrices, yeah? Okay, this is just what we just emphasized. And what else do we have here? Like basically, so we have two matrices and A and B, okay? No, there is no need to show them anymore. But this is just to show you certain exploration of the relationship between trace and, you know. So what am I having here? np.trace of A plus np.trace of B is going to be equal to np.trace of A and B, yeah? Well, of course it is going to be, yeah? And you verify it here. So if you think about it, when you have two matrices, when you add them together, obviously all elements are added together, so that the diagonal elements are just added on top. So when you do a trace which sums all of that, it's going to be the same thing. And how about this? So nb trace of A multiplied by 2 is equal to 2 multiplied by trace of A. And that's true as well. Okay. So that is basically just a basic introduction into how we use Python and NumPy, like very basic stuff, how to work with matrices. But of course, we will be expanding further as we go along through this lecture series. Well, I'm hoping that you have enjoyed this lecture, and I look forward to seeing you in the next class. Take care and all the best.